At its core, we all know that it's the transformer that play all the important properties and also have all the interesting structures that can enable all these applications, right? And in these transformers, we all know that the difference between the transformer and the multi-layer perception is that there's an attention layer, and this attention layer actually plays some magic, right? So for the attention layers, we know there's a query, there's a key, they do interproduct, they can compute the softmax and use these softmax values to reweight the embeddings from the previous layers, and you do this multiple times, and magically it gives you very nice outcomes by predicting this next token. So then the majority of this lecture is going to contribute and to talk about how we should understand this mechanism. So we basically talk about two papers. There's one paper called Scan and Snap that is being accepted in Europe 2023, and we have a follow-up paper called JOMA as accepted in ICDCS iClear, talk about understanding transformers. So we start with the Scan and Snap paper, which basically understand attention in one-layer settings. So we always start with very simple settings in order to understand the mathematics formulation and structures in order to have a better understanding for multi-layer transformers. So we start from the one-layer settings. In this one-layer settings, we have a very simple input-output, right? So the input here is basically a few contextual tokens, x1 all the way to xt minus 1. And then you have a last token, which is called a query, and that's sent to the query, and you do self-attention. And once you have some distribution across multiple tokens in terms of the probability, in terms of the attention scores, you use this attention score as a weights to compute the output features. And this feature is going through normalization, and then decoding layer, and there's our softmax, and use that to predict the next token, xt plus 1. So that's basically the model, very simple model. And here's the formulation that we try to use in order to build this end-to-end mathematical structure there. Right. So based on this one, and you're going to see okay, if you write them down literally, you're going to see a lot of parameters. And you see WQ, WK, and you also see U. So it's very complicated. If you write them down and try to compute the gradient, it's very messy. So we actually make two very important tricks. So first of all was that you want to make sure that you reparameterize the problem with independent variable. And this has turned out to be very important for this paper and also for the follow-up work that does more better understanding for multi-layers. So this is actually try to reparameterize these many variables into Y and Z. So Y is basically the top layer, the decoder weights, and Z is the pairwise logits of self-attention matrix. And then suddenly the dynamics become easier to analyze, and we can actually come with some conclusions. So that's basically the major first step. We can do that, and we can actually use that to write down the dynamics of Y and Z. I'm going to cover that later because this equation seems to be very complicated. So in the next few slides, we're going to have a much simpler formulation after we have introduced JOMA, and then we'll put them together, and magically things become much easier. We first start with the conclusions, right? So we don't want to go into details first, but talk about what is actually bring us for the property of transformers. So here are a few major assumptions for the Scan and Snap paper. First, there's no positional encoding. We don't talk about positional encoding right now because first of all, it's a little bit harder to deal with. And second, we actually see people have papers that can show that even without positional encoding, you can still get reasonable performance, right? And second, the sequence length goes to infinity. You have very long sequence length. And third, which is a particular assumption in the Scan and Snap paper, is that the learning rates of decoder Y is larger than the learning rates of the self-attention layer Z. And finally, there's some other technical assumptions. So, and on the data distribution, we also have some assumptions as well, right? So we assume there's a bunch of sequence classes from 1 to K, and for different sequence classes, there's two different kind of tokens. There's one token called distinct tokens that only appears in one class, but not the others. There's also common tokens that appear in multiple sequence classes. Right, so you can basically write them down in a mathematical form, saying that for distinct tokens, the probability of that sequence of that token, given the sequence index is greater than 0 for only one sequence class. But for common tokens, this might appear on multiple sequence classes. Right? So basically, that's the assumption. Okay, given that data assumption, then the question is, how does the self-attention layer behave? Right? So here's the main conclusion. It's the overall picture of the transformer dynamics. So first of all, we try to put this key statistics there, which is called the CL titer. That is actually the product between the co-occurrence probability, which is the probability from a data set, and also exponents of the pairwise attention matrix. Right? So you have this C theta here. You want to analyze the behavior of the C theta. So, and you're going to see like for distinct tokens, this C theta is non-zero for just one class, because the corresponding co-occurrence probability is non-zero for only one class, but not the other. So you're going to see very distinct patterns. But for common tokens, it appears in both of the sequence classes. And then the first conclusion is that for common tokens, you can analyze its dynamics, and it shows that the gradient will basically drag all the attention score of the common tokens error to be smaller and smaller. Right? So Z will become smaller and smaller because the gradient of Z with respect to time is smaller than 0. So here, this notation means that it's time derivative, right? So time derivative of Z is smaller than 0. Right? So then over time, this U becomes smaller and smaller. This is true for common tokens, basically the token that appears in multiple sequence classes. On the other hand, you can actually show for distinct tokens, their corresponding Z, which is the attention logits, will grow over time. Right, so this is basically the figure showing that how it grows. Right, so for all these distinct patterns, distinct tokens, their attention score will go up, and this increasement of attention score will also make the final C theta going up as well. Right? So from these two, you can already see the attention mechanism is kind of like the learnable TF-IDF. Right? So if people have been working on NLP before the transformer era, and people may have heard about this TF-IDF kind of formulation, which means that you want to find tokens or find words that has a high frequency, but also want to have the words that has inverse document frequency. Right? So the first term talk about very important words for each class. And the second criteria basically ask the model to filter out the tokens that is too common across multiple documents. Right? So for example, and also all the articles, all the common words, and they are not informative. So they should be suppressed when you are doing a decision document classification. Right? So on the other hand, if you have very specific tokens for specific categories, then we should pay attention to. Right? So for example, if you talk about sports and talk about Messi, then Messi is a very important token for sport, and then you have the connections there, and you may use that to do a better document classifications. And furthermore, we can actually quantize the growth rate of the attention scores. Right? So basically, ZML, which is basically the one element of the self-attention matrix, and this is actually a function of time. This actually will grow faster with a larger conditional probability error given the attention, given the sequence class. And we can actually characterize how it grows faster. So we can have a theorem. The theorem will tell you the ratio between the two distinct tokens, how much they grow and how fast they grow. So the figure also shows that if you have like a distinct tokens that has a very high co-occurrence with the query, then it will grow much faster than the distinct tokens that only happens to be co-occurred with the token, but it's not with a high probability. So you're going to see this very high jump when you're doing the training. Right? So in some sense, this is called the contextual sparsity, because over time, you're going to see this C theta, which is attention score, will actually become sparser and sparser after normalization, because the winner will become richer, the rich will become richer, while the poor will become poorer. Right? So, and over time, you're going to see maybe one or two where it stands out, and this is the reason why you see attention become sparser and sparser during the training. Right? So that's and why we are calling this contextual sparsity is that this depends on the query. for different query, you're going to see a very different curve there, right? So for different query 1 token, this will have something like that. From a different query tokens, then maybe a different token will have high co-occurrence with that particular token, then you will see a very different patterns. That's the query-dependent sparsity there. And finally, we actually have shown there's a two-stage effects for the attentions, right? So people may wonder, according to this picture, then over time you're going to see a higher and higher growth for higher co-occurred tokens with respect to the queries, and eventually you're going to see a winning-take-all effects. But actually, it's not the case. In our analysis, we eventually will show there's two different stages. One is called attention scanning, in which this winning-take-all effect is happening. On the other side, the second stage called attention snapping, in which everything slows down a little bit, and finally things saturates. Right. So once you see the rich become richer effects, and after some time, the attention pattern will freeze, and it become kind of like a minority take-all kind of picture, but it's not like a winning-take-all. So that's basically the overall picture that is shown by the scan and snap paper. Right, so that's basically the main picture. And we have a few different simulations and showing this is really the case. Right, so and this here is like some overall strategies for the theoretical analysis. So if people are interested, then here's like a very simple strategy in how to prove that. Right, so first of all, we want to use this power of infinite sequence length to basically turn all the terms into statistic terms that include the probability distribution. That's the first step. And the second step, because we have the assumption that the learning rates of Y, which is the decoder, is much, much faster than the learning rates of Z, which is the self-attention matrix. Then you can basically treat the self-attention matrix as a constant when you're analyzing the dynamics of the decoder. And then once we have that nice equation, which tell you that how the gradient backpropagate to the attention layer is related to the data that is being fed into the decoder, then we can plug this back to the self-attention layer and then analyze what's happening in the self-attention. Right? So that's basically how you analyze the two-layer structure of the one-layer transformers. So we have done some very simple real experiments. For example, on Wikitext2, if you have this kind of like a learning rate structure, then over time you see very sparse patterns in attentions. And if you do a lot of work in practice for training transformers, you will see this learning patterns changes. Right. So that's basically the scan and snap paper, very simple. And then we can talk about like how can we improve scan and snap paper and how to get rid of these assumptions, right? So we have annoying assumptions here, right? We say there's no embedding vectors, there's no residual connections, right? So the decoder need to be learned faster than the self-attention, which never happens in practice, right? So and we have this single layer analysis, right? So how to get rid of them? Then the next step is to introduce the work called the drama, which is our second follow-up paper that try to understand this dynamics much better compared to the previous papers, right? So in that paper, what do we do here is we actually discover some very nice properties of the training dynamics between MLP lower layers and also the self-attention layer. We combine them together into a layer called the modified MLP. So that layer actually capture the dynamics of both of the layers, and at the same time, much simpler than if you think about the self-attention and also MLP layers at the same time. That's basically the rough idea about drama. So for this one, we basically drag one layer of the transformers, right? And then we put like a bunch of symbols to analyze what's going on. So note that we now think about like this additional rest connections here. And this rest connections is basically like is missing in the previous analysis. But now we can add them back and show how it actually played the role here. And we also can use these nonlinearities. So this phi is nonlinearity in the decoder layers. In our previous scan and snap paper, there's no nonlinearities. It's basically linear towards the softmax. So that's the difference. So we actually can able to show a nice properties there. And we also have this embeddings matrix U here. And for the embedding matrix, we basically have assumption that these embeddings are orthogonal to each other, and that does not change over time. Right, so that's actually an assumption that's being questioned by the reviewers. So that's why we have a figure showing in practice, this is indeed the case when we actually plot the similarity between embedding vectors at different layers for models like a Pythia. We also tested on other models. It looks also quite true. Right, so here basically the figure showing that x-axis is is basically the mini batches, right, the training dynamics, and the y-axis is cosine similarity. Right, the cosine similarity will vary between 0 and 1. Right, so 1 means like a perfect line, and 0 means like orthogonal to each other. Right, so then what you see here is that over the training, the cosine similarity does not really increase that much, right? So it's basically at roughly like 0.03 something, right? So it's almost orthogonal to each other for even for different layers. And here, each curve corresponds to different layers. The layer is represented by the color of the curve. Right? So then basically means that this orthogonality assumption is approximately true, but still we haven't analyzing the dynamics of embedding yet, which may be the next paper. So given these assumptions, then we actually will see there's a joint dynamics between the lower layer of MLP and also the self-attention layers, right? So you can actually compute the self-attention from the basically like the magnitude of the lower layer of the weights. Right, so this basically means that once you have that equation, then you can forget about the self-attention layers, but just plug in this equation into your dynamics, and it will give you something like that. So this equation basically tells you the story of both self-attention plus the MLP lower layer. Right, so then you can use that equation to analyzing the dynamics of the transformers. That's basically the idea. So this actually makes it much simpler, and this does not require the assumption that the decoder layer is much more is basically training much faster than the self-attention layer. You don't need that anymore. So here's basically a few slides that try to do comparison between scanner snap and the drama. This is basically a few additional slides that we add in order to answer the question raised by the students. So here's like a general formulation that try to combine the two things together, right? So here we basically have a unified general formulation that combine these two things together. So here's like you have these notations, and here common assumptions between the two papers. Basically, all these common assumptions. First of all, the lower layer weights W, and also the self-attention layer weights Z. They are both trainable parameters. They can be trained, right? So we basically in both of the work, we are not considering WK, WQ, WR, WK, WQ, WV, but we are caring about this entire Z matrix as a trainable parameter. So this is something that is different from what's practically happening. And second, this U, which is embedding, is fixed and column orthogonal. Right? So this is also another assumption that we make for both of the two papers. And the third paper is that the input token, one vector, is actually one hot column vectors, so that we can actually compute the frequencies. Right? This is true definitely for the first layers, in which like each of the tokens is being encoded by one hot representation. Right, so, but it may not necessarily be true if you think about like multiple layers and in terms of like the intermediate nonlinearities, right? So this may not be necessarily true. So the difference between scan and snap and the drama is that you might have very different settings, right? So for example, in scan and snap, you might have additional normalizations, L2, and you have to assume that this activation function is linear, right? And ZW learns much faster than Z, right? But on the other hand, in drama, we are having different settings, right? So maybe phi is identity, there's no normalization, right? But in nonlinearity, you can use linear or nonlinear, right? So we can also, there's a bunch of other different directions. And this is actually the derivation in one slide about the first theorem. So I don't want to go through that, but I just use that as one of the summary of the theorem one. If people are interested, you can go through that. This is actually much more concise than the proof we put on the paper. And we're going to update that in the camera ready. So then people will say, okay, what's happening to drama if you have this drawing dynamics? What happens? So here's one verification about dynamics, because in the self-attention layers, we actually make some assumptions. We want to make sure the assumption is true. And once we have this drawing dynamics, then we can try to come back to the scanner snap settings in which the activation is linear, and to see like whether it actually having the same prediction as in the scanner snap. The answer is yes, we can actually have the same, very similar predictions there. So the prediction basically say that attention will become sparser. It's consistent with scanner snap, and the component that has the highest token, highest like this token discrepancy times co-occurrence. So this is a term. If the term is highest in terms of the in terms of magnitude, then you're going to see the curve will go the fastest compared to other curves, which will saturate. Right, so it's actually consistent with scanner snap. But what makes things more interesting is if you can extend this drama to nonlinear activations, in which like activation is nonlinear, then the previous scanner snap paper is not able to give you anything. But we actually can give you a much interesting behaviors that is correspond to nonlinear activations. It actually tell you that the attention will first become sparser, which is what the scanner snap paper will predict. But at the same time, it will become denser later in the later iterations. Right? So basically, this is the difference picture. The picture is different between the nonlinear activation and in the linear activation. In the linear activation, I mean, the attention will only become sparser, and then it goes sparser and sparser until it saturates. But in nonlinear situation, it will become denser later. Okay, so this is actually, I don't want to go into details for this one because there's a lot of math there, but we first want to check whether this is consistent with the real experiments. Right, so actually in the real experiments, we have trained our transform models, multi-layer version in two different real-world text, real-world data sets. One is Wikitext2 and the other is Wikitext 103. And you're going to see exactly the same curve as predicted by the theory. Right, so especially in the first layer, if you train a one-layer transformer with non-narratives, then you're going to see it first drops and then go back again. It is very similar to the previous curve that is drawn by the theory. Right, so it's very similar. And if you put like multiple layers there training, you're going to see very similar curves as well. Right, so especially in the top layers, you're going to see things drops and then come back. Right, so that's actually quite interesting. Right, so and then we want to really understand why that's the case. Right, so why you will have these behaviors? Because these behaviors doesn't seem to be that intuitive, especially for one layer. Because for one layer, it should be the case that we just do one shot. Why you need to pick up the features that are not salient later, right? So first, like the things become sparse because of the same mechanism as what's happening in the scanner snap, that the token that co-occur a lot with a query, they will basically be picked up. And then the attention will go up, and other attention does not change or even go down. Then that's why you see the attention entropy goes down to very low numbers. But after a while, the attention score will pick up, the attention, the entropy will go up. The reason why it go up is that it also pick up features and tokens that is not salient, but still reasonably salient over time. And that's why you see the attention entropy also goes up a little bit. This does not drop in the first step because here the unit is mini batch K, so kilo mini batches. Right, so basically it has to be a go from like from the first 1 kilo mini batches. It drops down, and after that, bring back up again. Yes. Yeah. And I think the scale probably is not important because you can always change the learning rates. You get different scales. Yeah. Yeah. Okay. So you also see the real experiments with other models, right? So and you see the similar behaviors as well. So the reason why we actually see this is because we have a hypothesis later to talk about these properties. So basically, this property is not useful for one layer, because in one layer, why not you just learn all the features in one shot without having these kind of interesting properties? But it may be useful in multiple layers. The reason why it is useful in multiple layers, we have to think about hierarchical data representation, right? So we think about, we want to learn a hierarchical data representation from the data, right? So in the representation, what happens is that you only see the final labels, okay, that's top layer. You only see the lowest tokens, which is in the lowest layer. But you don't really see what's happening inside, right? So there's latent variables that will govern the data generation process. But you don't know. We have no idea what's happening with our data set, but you really want to train a transform model so that the transform model can learn automatically the latent representation in the data set. Right. And what's happening here is that we're going to hypothesize that in your transformer, the reason why you see this attention jump up is because you actually can learn the latent representation there. So first of all, you can actually prove a theorem. The theorem basically tells you if you have two tokens that is very close in hierarchy, then their probability that they co-occur will be very high, almost equal to 1. But if you have two tokens, L prime and M, they are very far away from the hierarchy, then their co-occurrence will be low, very close to 0. So here's like an equation that characterizes this behavior. H is basically the height of the common latent ancestor of these two tokens, L and M, right? So for this L and M, their common latent ancestor, H, is 1, is very small, right? So that if you plug this in, then this is approximately 1. If you use this same theorem for H, for L and M, L prime and M, they are very far from each other. And their height of the common latent ancestor is almost L, which is the total height of the hierarchy. Then this probability will almost become 0. Right, so first of all, you have this assumption. You have these interesting properties for the hierarchical generative models. Right, so note that this property has nothing to do with transformers. Okay, then we think about like how we transformer should learn it. Right, so you think about this property that we first learn tokens that co-occur a lot, then we learn tokens that co-occur sparsely. Right, so this mechanism actually works well for both shallow and deep latent distributions. Because for latent distributions that is deep, then what we learn is that we first learn M and L associations, and also M prime and L prime associations at the same time, because they co-occur a lot with each other, according to our previous analysis for the hierarchy. Right, so because they first learn the two, then you automatically implicitly build a hierarchy that can be later combined again in the top layers. Right. So you basically avoid the learning of M and L prime, which may have co-occur a little bit, but their co-occurrence is not important and can be learned indirectly by the hierarchical learning. Right. So then that's actually give you the intuition why transformers should learn the features in this way. Right. And on the other hand, if you think about if the data is generated by some shallow latent distributions, there's no much hierarchies there. We just have very straightforward distributions there. Then what happened to the transformer learning? So the transformer will first learn the tokens that occur a lot, M and L, but eventually it will learn a co-occurrence between M and L prime, right? Because these two still have some co-occurrence, but maybe very weak. Then basically the same mechanism, which is attention mechanism, can learn both the deep latent distribution and also shallow latent distribution at the same time without knowing the internal structure of the data. So this basically provided you with kind of insights about why transformer can do so much interesting things without actually knowing the inline distributions. It will be auto-adaptive to the structure of the data. That's basically the explanation why we see this attention first go down and go up again. Right. So if you come back to the figures, and you will see interesting behaviors. If you train the same model, the model with the same data sets, right? So you train this first layer model, the one layer model with transformers, you see very deep, very very interesting structures there. And this is very obvious. But if the layer of the transformer become more, you have like more deep transformers, then in the lower layer, they go basically drop, but there's no backup. Right, so but in the top layer, there are still kind of like a bouncing back kind of properties. The reason why this is the case can also be explained by this theory, right? Because if you have multiple layers of transformers, then what you do here is that you first learn this co-occurrence that co-occur a lot, and once you learn this, you don't need to learn the weak co-occurrence between A and M prime again. Because you don't need to learn these two co-occurrence, then you don't have this bouncing back properties. Because this bouncing back property has already been explained away by the previous mechanisms, right? So that's the reason why you don't see the curve in the lower layer that bounce back after if you learn the data with multiple layer transformers. Yeah, so I think right now this is a theory I have in mind. But we haven't tested any other possible explanations. Okay, I see. Yeah, I'm not aware of other papers that come up with to explain this. Yeah, right now. But I mean, it will be interesting to see any alternative theories there. Yeah, that's just one way to explain. Yeah.
Is there a way you can generate some synthetic hierarchical data to prove this theory?
Yeah, so you can actually do that in one of the experiments, right? So because for this theory, one possible implication is that over time, you're going to learn these latent variables in different layers of the transformers, which is indeed true for our analysis. Because if we can generate hierarchical data from synthetic experiments, you can use transformers to learn it. You actually see almost 100% correlations between the latent layers, between the hidden layers of transformers and the latent variables, especially in the first few layers. You can see we have tables in the paper. First of all, the causality here is not related, right? So we don't know whether the causality will play a role here or not, because here we only analyze correlations. There's no causalities. Yeah, but indeed, it seems like it will learn strong correlation first, and that strong correlation may mean causalities, because if you see these two tokens happen a lot, then they might have real correlations between the two. Yeah, so I think we explained a little bit previously. So if you only train the data with shallow transformers, you see very clear bouncing back. If you train deep transformers, then the lower layer, once they drop, they will not bounce back, because the bounce back means that the lower layer are trying to learn features that are weakly correlated. Right? If these features are already being explained away by the top layers, the lower layer does not need to learn them anymore. So that's why it only goes down, but it never goes up.
Well, then my question is, if you unfreeze them after, let's say, 1 or 3 epochs, whatever it is, do you think that it's going to become, the lower layers are going to be the same level of, it would have bounced back and would it stay there, or do you think it would go back down, and then the higher layers would be?
Yeah, that's a very interesting experiment to try. Yeah, I would suggest it's possible that you're going to see the lower layer bounce back and then go down again. Actually, I saw this curve in some of the configurations. Yeah, so it's actually pretty interesting. And there's also other experiments that shows by training the different learning rates, you're going to see very different kind of training curves. Right? And the training curve that show these bounce back properties will have the highest validation accuracy, which means that that might mean the correct way of learning data. Right? So compared to other kind of learning rates. Yeah, you can check these experiments in the paper. We haven't shown this yet. It depends on how you define your causality, right? So it's possible that the causality would mean if you kill the first in promise, and it will not happen, the second will not happen, right? So, but not vice versa, because it's asymmetric, right? So if that's the case, then you might want to design properties that to enforce the attention matrix is also has the same property, something like that. It's possible. Yeah, I think that's actually a very good question. So we actually try our parameterization, the parameterization Y and Z in practice. Then what happens is that it can still learn, but performance is obviously not as good as the original transformers. Right, so we actually have one called the YZ transform, which is the YZ parameterization that we've shown before. You can actually train it for 3 layers. It actually works. But when you train multiple layers, it actually does not work as well. This is because the power of embedding. Because in the YZ transformers, there's no embedding. The embedding is all put into the Z matrix. The Z is like huge. It's a vocabulary size by vocabulary size. Right, so but this huge matrix may not be trained well doing the practical training. In practice, what we do is we do not really like train this huge matrix, but instead we train embedding and also the weights to basically mimic this huge attention matrix. This is in some sense much more efficient. So this aspect hasn't been explained by the theory yet, but hopefully in the future we're going to explain how the dynamics look like for the attention for the embedding matrix. So we have to basically break this into parts and analyze one after another. Yeah, I think that's a good question, because the reason why we want the assumption for the Skinner snap paper is that the formulation is a little bit restricted. So you really need to analyze 2 extreme cases, right? So either a token is happening in multiple classes, or a token only happening in one class, right? But there's actually a lot of things that's in between, right? So we say like one token happens a lot, 90% in one class, but not 20% in other class. What happens to that, right? So the good thing about drama is that once you have that formulation, then naturally you will have this kind of property. This property is replacing the common token versus the distinct tokens. Now we have a continuous spectrum covering all the tokens, right? So if this quantity is high in magnitude, then this is distinct tokens. If this quantity is almost 0, then it's common tokens. Right, so then you have a spectrum that you don't need the assumption anymore. Yeah, so that's the good thing about the formulation. Yeah, so you still have the occurrence and also this discriminancy. So it's a similar thing as in the scalar snap, but now it becomes a natural term, and that term does not need to be specially treated. Okay, so we have covered mostly the 2 theory paper in 40 minutes. I think for the remaining 20 minutes, we're going to talk about more empirical work. So I'm going to skip all the formulation details, and hopefully people have enough of it. Yeah, so I think it's great that we have so many questions here. Usually for theory, it's pretty hard to understand, but it can be interesting to discuss the future work. And of course, the future work here is that we want to do embedding vector analysis, right? So in these 2 papers, we basically assume the embedding is fixed and is orthogonal to each other. While this is true if you check the empirical results, but it's still not ideal, because the embedding should also be learned during the training, but we haven't tested it yet. We haven't really analyzed what's going on with the embedding, so which is a little bit a pity, right? So, but there will be a next paper trying to deal with that, and also positional encoding is another one, right? So, and also we want to talk about basically the dynamics of the latent concept learning, right? So, in the multi-layer settings, we basically give a concept about how this should learn, but there's no concrete theorem telling you how this latent vector get learned over time. But this is pretty tricky, very hard to deal with. Okay, so I'm going to, so this is another, but this is in something unrelated slide talking about some interesting properties predicted by drama. I'm going to skip that. So this is tell you when one vector in the MLP layer can encode multiple different patterns. It is called a pattern superposition. So this is actually being observed by many empirical works, and also being highlighted by one of the paper from Anthropic. But in drama, we actually can also analyzing that and show that this is indeed possible if you train from scratch following the training dynamics. But I'm going to skip that. Okay, so let's go to the second part, which is the application based on attention properties, mostly on the attention sparsity. So for this, we have a bunch of papers. that try to leverage the sparsity in order to make the inference faster. Right. So hopefully from now on we are talking about empirical results, and hopefully the cognitive load for audience is much more relieved. So the occupancy is very simple, right? So we want to only keep the high activation tokens in attention and MLP and use that to accelerate the inference of the large neural models. Right. So you are, empirically, what you see is like you see a lot of heads that's not activated for each of the forward paths, and you also see a lot of MLP layers activation is also not activated. That's actually not great, because this means that the corresponding weights are loaded for nothing. Right, so then in order to solve this problem, we propose what is called déjà vu. That paper basically tell you, okay, how can we predict which head is not activated during the feed-forward inference. Right, so for example, this head is 43 is not activated. It's basically giving you uniform distribution across tokens. While head 42 and 44, they have like a very clear patterns. They have a very clear focus in terms of their distributions. Right? How you predict that? So we actually learn a very simple kind of predictor per layer, and also per heads, and also per activation, and about like which heads and which MLP intermediate layer should be activated. Right, so and we basically use that to predict this contextual sparsity, and use that to make the forward faster. It's very simple, right? So the reason why we want to predict that is because if we know in MLP layers only the second and the sixth activation will be activated, then we only need to load the corresponding rows and columns of the two weights. Right, so this loading is much faster, because you have a fewer number of ways to load. And we all know that in GPU, loading memory to cache is very, very slow, probably like a few hundreds of GPU cycles compared to you actually compute. When you do computation, it's actually a few cycles usually, so much slower. So if you can load like a fewer weights, you actually will have a much faster feed-forward speed. So you actually can do that, and you can basically like do all the engineer work, and this is final performance, right? So we actually can make make this kind of feed-forward faster than different kind of benchmarks, right? So if you compare this with Hugging Face and also with fast transformers, it actually has like lower latencies, right? So that's basically one of the ideas. And it's compatible with the quantization, right? And also can be useful, especially for like a lower batch size. So we also have a paper called H2O that tries to leverage sparse attention for fast inference, right? So we all know that if you compute the attention, it's actually n squared. Right, so basically, for each of the new tokens you want to compute the attention, you have to go through all the previous tokens. It's n squared. But the question is like, do we really need all the previous tokens? And the answer is actually no. Right, so if we actually draw this distribution, right? So how many tokens actually has higher activations, and how many tokens has lower activations? You actually will see, first of all, this attention score distribution is very similar to the co-occurrence, which I talk a lot in the previous slides about series. This also is a good empirical justification about correlation between the two, right? And also, we also find that if you get rid of this token that has a lot of attention, then all of a sudden the downstream task performance drops substantially, right? So these tokens that happens a lot and has a lot of attention for this feed-forward path. We call these heavy hitters. So if we use these heavy hitters in our inference, they have good performance. If get rid of them, they have very bad performance, right? So then the natural algorithm becomes, we will keep the heavy hitters, but we get rid of all the rest tokens that is having a very low attention scores. Right, so this is the attention algorithm. It's called H2O, heavy hitter oracles. That basically is a local greedy algorithms. Every time you sum up the score of the previous tokens every decoder step, and you basically drop the tokens that has the lowest accumulated attention score from all the previous runs, right? So you only keep like a budget of your KV cache tokens, and you get rid of the tokens that is fall below the bar for the cumulative attention score. That's basically the idea, very simple. And you actually see very good performance, right? So you'll see like you only keep 20% of the KV cache tokens. And surprisingly, you actually have almost the same performance in multiple benchmarks, right? So if you only keep, for example, like local tokens, it actually drops a lot. But if you keep only heavy hitter tokens, it actually gives you very comparable performance until you drop more than 80% of the KV cache. So this will save both the memory, because you don't need to keep the KV cache, and at the same time you also make the inference much faster. Okay. Yeah, so we also see it has actually other benefits, like it will give you more creativity, because it gets rid of some of the tokens that might restrict your creativities. Yeah. And natural question is like, okay, what are these heavy hitters, right? So, and we actually do some further analysis, and this actually leads to a paper called attention sync. That's called the self-attention. That's called the streaming LLM paper, which also is accepted in this year's iClear. So we basically say, okay, what are these attention heavy hitters? It turned out that many heavy hitters are actually the first few tokens in the transformers. And they actually occupy a majority of the attention score, right? It's like 50%, very, very high, very much. So then what happens to that, right? So then like we basically have this hypothesis. Maybe in some cases, in many situations, we don't need that attention that sum to 1, but it has to sum to 1 because the softmax rule. Right, so they basically like overload multiple very strong attention scores for the initial few tokens in order to do that. And it turned out that it doesn't matter whether these first few tokens are, I mean, you can replace the first few tokens with just like with just return. It will give you very similar perplexity. However, if you get rid of the first few tokens, all of a sudden the model just breaks. Right? The perplexity always basically goes up to like 5,000. Basically means that it basically gives you garbage. Right? So basically the first few tokens are important, but only their position is important rather than the content. So this discovery is very interesting, and we later find that if we only keep the first few tokens, you can keep infinite chat with the models without having restriction of the context windows. That's actually pretty important for empirical distribution and deployment of the larger models. Yeah, so that's the streaming LLM paper. The paper basically have a lot of attention from external world, and the people really appreciate that. And some of the variation of the work has been deployed in hardware devices and also libraries. So, and here's a very simple idea, right? So when you generate like next tokens, you first keep like a KV cache budget, which is fixed length. If your token generation exceeding the KV cache budget, then you get rid of these tokens that is in between, right? But you keep the latency tokens, the recent tokens, and also the initial tokens, as well as keeping their attention position in the cache rather than in the original window. And this basically gives you infinite chat capability for the models, right? So with streaming LLMs, you will have infinite chat and all the texts, they are reasonable. But of course, if you don't use streaming LLMs, then what happens is that you either run out of memory because you have to keep like a very long sequence of the KV cache, or if you just truncate all the previous tokens, including the initial first few tokens, then the model suddenly will break and will give you garbage after the first few tokens are out of your budget window. So that's actually quite interesting. Yeah, so and we have tested thoroughly in many different scenarios, and we see that our streaming LLMs can give you very stable perplexity, which means that the output is very meaningful, right? And at the same time, it saves memories. It keeps constant memory over time, even regardless of the context window, right? So you want to keep the budget and you keep the first few tokens. That's it, and you can keep chatting with your larger models forever. That's the interesting properties there. And we have a bunch of experiments. You say it can scale up model to 4 million tokens, and you can scale up to maybe more than that, and with the same perplexity, which is good. Yeah, and also we compare with other baselines. Yeah, and you also want to understand what's happening to the first few tokens. So what happens if you actually treat these first few tokens as learnable? And you can see like the learnable token actually do the same thing. And you can actually do even a little bit better, right? So you have a dedicated token called sync tokens at the beginning. And you also keep the sync token either a zero embedding or learnable embedding. So that's correspond to the zero sync and the learnable sync. And you see that after the sync token is there, all of a sudden the perplexity become very low, and you can actually chat with the models without having issues with the length of the context window. Yeah, so we also see concurrent work, which is also from Meta. Interestingly, that we don't talk to each other for different departments, and when we submit the paper, we see very similar ideas from different groups, and they also find very similar structures in the vision transformers, which is called the vision transformers need registers. Register is corresponding to the attention sinks. Yeah. So of course, like it actually does not solve the long context. It just drop tokens and keep the perplexity. But if you want to do any kind of like a series, like a passcode retrieval, it will not give you the right answer if the token that corresponds to the answer is being dropped. Right? It's basically keep the perplexity. It means that it will give you reasonable answers, but it may not necessarily retrieve the information that is being discarded. So that's basically the limitation. And hopefully, in the future, we're going to do that as well. Yeah. And finally, basically, like I want to introduce another paper that they try to solve the long context window, right, by basically doing fine tuning. So that's basically one possible. Oh, sorry, that's actually this paper. Yeah, that's the paper. So in between, there's a streaming H2O, which means that you want to combine streaming LLMs with the H2O approach, right? So if you think about streaming LLM, it's actually a special case of H2O because streaming LLM only keep the first few tokens, where H2O will pick the token based on their attention scores. Right? You can combine the two, and you actually will give you even better performance. Right? So and at the same time, you will keep the infinite chat property. That's my very recent updates. So using this, so welcome to use with all these improvements in the fast inference. So and finally, there's a paper called Extending the Context Window. So this is actually a paper that is always in the archive version, because after 2 days of its release, we see Reddit, we have people have better ideas how to solve the problem better. So just 2 days. I just say to be precise, it should be like 30 hours or something. So we decided not to submit a paper because it's just too much competition. Yeah, so this is actually a paper that tries to extend the context window with pre-training, right? So we all know that the context window cannot be changed after the pre-training. Once it, for example, for Llama model, the context window is 2K. If you try to use it beyond 2K, it suddenly gives you garbage. So that's basically the problem. And then how can we extend it? We can obviously fine-tune it with longer text, but fine-tune will require a lot of resources and a lot of mini batches. So we actually find that by changing just single parameters in the Llama models, you can make the fine-tune much more efficient. Right. So this is actually very simple. We basically say we basically change the positional embeddings scale, and you scale this back to the original size. Right. So for example, your model is like 2K. If you want to scale the model up to 4K, what happens to that? You basically say, okay, instead of like doing anything, you just say for each positional encoding, you just divide this positional encoding index by 2. Very simple, right? So then for the 2K window, it will map back to the for the 4K window, it will map back to 2K, so that each of the positional encoding become the positional encoding, the interpolation of positional encoding in the previous layer, in the previous version, and use that, change the transformer, you train the model with only a few, only with like a few hundred samples, and all of a sudden it does very well. Right? The reason it is the case is because we actually discovered that the attention function is actually well behaved. Right? So if you do interpolation, it behaves quite well. But if you do extrapolation, and all of a sudden it gives you super bad scores out of the window that is being trained on. Right? So that's actually the reason why we should do interpolation rather than extrapolations. Yeah. So that's the reason. And if we use our approach, then we can actually train models that can extend to long context windows with less than 1,000 steps of fine-tuning. And you can extend it to up to 8x length of the original context windows. This is actually much more efficient than if you just do hard fine-tuning without changing anything from the models. Right? So for example, in this case, 200 steps suffice to extend the window from 2K to 8K, 16K, or 32K, right? So you only need like 200 steps. But like if you just do fine tuning, then you really need like fine tuning. You really need to like more than that. Right? You need to basically use like maybe 1,000 steps, but still you don't really extend it to 8K. You only extend to 2K, 2.5K, right? So it's much more efficient if you do interpolation in the positional encoding. Yeah, and still the performance does not really drop that much. I mean, it stays approximately the same for all the benchmarks. Yeah, and as I said, I mean, after the paper got released, 2 days, you guys something better in the Reddit. That's how intense competition is. And we actually see many more papers coming out along that directions. Yeah. So I hope like people benefit from these insights. And that's basically all of my guest lectures. Thank you for your attention. Yeah.
What do you mean this interpolation, extrapolation in this language model? What does that mean?
Yeah, what that means is like very simple. You start from, for example, the window is 2K, right? So 2K means that for each of token, you will first assign an index in terms of the position, right? So from 0 to 2K minus 1, right? So and then given the index, you can compute their positional encoding. So for this one, we are using rope. Right, so that's basically the one that people use for all these models. So to compute that, you first subtract these two positional encoding to position index. And then use this m minus n number, and you basically plug that into this equation, right? And you can compute the attention based on that. Yeah, that's basically how you use a position to do positional encoding.
So I think the first question is about how can we connect the insights from the theoretical papers with, for example, the scaling law and also emergent capabilities of large language models.
Yeah.
Because the theoretical pictures from the papers, I mean, they are not completely absent from earlier models.
You mean like how you combine the two in larger models? I think people already use that, right?
How do these theories explain, when we train much bigger models, we get much more stronger, emergent capabilities.
Oh, I see. Okay, so I think there's definitely for theory, theory is actually a very deep stack, right? So you have a series that is mostly like empirical and also try to describe the phenomena. I would say like scaling laws and also emergent behavior. They are series that's more on the kind of like summarizing what's happening. Right, so this theory definitely is very applicable to the current models. Right, so for example, according to scaling law, you can know if you scale the model by 10x, if you scale the data by 10x, what will happen to the performance? You basically have a curve. The curve will tell you to predict what's going on. Right, so that's actually very useful in many situations. Right, so and for the theory like this, so basically for the theory that we discussed here. It's more on the kind of starting from the first principles. right? Start from the formulation and then think about like, what is the consequence that will be achieved by the formulation, right? So this might be a much harder to be applicable to the actual applications. But if we do things well enough, then all of a sudden we know everything across for this entire process. Then there could be like many different scenarios that can be applicable. So it's a very hard journey, but maybe in the future it may come up with applications and very strongly. Yeah.
So what do you think is the most immediate next step from the first principle to things like scaling laws?
Yeah, so I think for things like scaling laws, what happened would be, so you're given like all the theoretical studies, and then given the theoretical studies, you might be able to simulate what happens if you have more data, right? So what will be the bound look like? And that will become a scaling law that you empirically observed, right? So this, in that case, it might be one step further than the scaling law that currently we have, and this is purely empirical. It's possible. I think people in physics has done that in many different scenarios. Right? You may start from first principle and come with some equations, and then say, what happens if you have 1,000 atoms? Have like 10 to the 32 atoms, and what happens? Then you come with kind of like a more global and empirical laws and try to fit this well the real world experiments. Right? So that might be one possible direction to go. It's the process really varies. I will give you personal opinions, right? So I started with doing some theories starting from 2017, and at that time it was a very painful process, I have to say. Yeah, so in that process, you might spend a few months on a problem that is impossible to prove, and even if you prove that, you don't really see any benefit of it. And you realize that what you prove is nothing. You don't need to prove that, right? So it's actually a very painful process at the beginning. But now, after a while, after maybe many years of exploration, then people may get to the point that you have good insights overall about like what is the rough picture about how the theory should go. And then, given the rough picture, you know what roughly the theorem should be proven. Some theorem. There may be some theorem. You can write them roughly. Even if they are wrong, that's fine. You just should write like wrong theorems, but they are approximately right, in the right direction. And then by adding constraints, adding conditions, and by like doing some more like empirical justification, you might have a better idea about what this should look like, until you nail down to an argument that is both logically correct and empirically useful. So that's probably like some way you can make the theory much more streamlined. Yeah. So for example, for the drama paper, we come with this idea, the core idea about drawing embeddings in maybe a few days, right? So once you get to derive that equation, okay, done, you get it. Then we know, okay, there's definitely a next step. Then we can do more work there. And all the work are basically like corresponding to that, right? So I have to say, like a series basically is not my like a major push. We have a lot of other work to do, but in order to, but there's already like a very good sense. Then you can derive theorems. You can think about like how to get like good solutions in a very short amount of time. So I think if we go through that process, then you will you have the capacity to do the theory, at the same time you can also do experiments. You also do empirical work. Yeah, it's kind of art. You have to say like you have to first try a few things, and then once you try, and then you realize that that may not be correct, right? So then you go to the different assumptions. It's basically a kind of process that go back and forth between your symbolic structures and also the real world structures, right? So you go from real world and then come with some assumptions, and then you come to the symbolic side and look at it and think about what should we do, and then come with, okay, symbolically, if we do these assumptions, then maybe it makes things easier. And you think about symbolically, okay, whether this symbolic assumption makes sense or not, right? And then come back to the practical side, and then do back and forth until you converge into assumptions that is both symbolically interesting and at the same time relevant to the real world. Then you convert to that, right? And over time, you become more and more good at that. Okay, I mean, first one that obviously like t goes to infinity, right? So that is the one that is being adopted. We have the collaborator. So the second author actually do many of the detailed work, and he first come up with a kind of confidence bound. If t is finite, I would say, okay, forget about it. Just say t goes to infinity, because that basically will capture the essence of the picture, while we do not care too much about the mathematical details, right? So in that case, these seem to be a good assumptions. Yeah, but I will never assume that your feature is fixed, right? That's actually not the right thing to do, even if this will make the mathematics much easier. This basically kill the entire physics picture. Yeah, that's not a good thing to do. Yeah, so there's always a balance. If you have a good assumption, you try it, but at the same time, like you make sure that the assumption does not break what you want to do. Yeah, so for this one, I mean, actually, I can tell you another story, because for hierarchical models, I have been trying to do something about that for many years. I mean, since my master degree, if you check my master thesis, it's about hierarchical representation of some vision models. That was a thesis, and no one read it. But anyway, it's a very long effort. And for CNNs, yeah, we also tried that if you check some of papers. So I have to say, like, this Java paper is the first paper that I do the hierarchical analysis and get accepted. All the previous hierarchical papers that we tried to do the analysis, they all got rejected because the notation is too complicated. Yeah, so it's very tricky. And for CNNs, yes, there's definitely hierarchical structures, and this is actually my motivation as well. Because I was originally a vision person. I mean, if you check my publications, I originally do some vision work, and obviously, vision people are obsessed with the hierarchical representations, right? So we have all these kind of insights there. But I think the difference between CNN and transformer is that transformer use embeddings, and embedding is very powerful. Super powerful. It's actually, I think one thing that you can think about that is that there's interesting properties for the for d-dimensional high dimensional space, right? In high dimensional space, you can put 2 to the d number of vectors into this space and keep all of them almost orthogonal to each other, right? But this is actually very nice properties. You can basically put like exponential content in or objects in this finite space. But if you do CNNs, and what happens is that you are essentially doing a one-hot representation for a concept, right? So you say maybe this token represents something, that token represents something. That's actually one-hot representation. But if you do one-hot representation, you want them to be orthogonal to each other, then you need a 2 to the d dimension, right? So this is actually very efficient. Another point that makes things efficient is that for transformers, it can also do lots of reasoning tasks. And the reasoning, I would believe, it's definitely related to representation of the embeddings. Yeah, so I would say maybe A can be represented by a summation of multiple embedding vectors. And the vector, one vector say it's a letter, the other vector say it's a first letter, the third vector will say it's a lowercase, or something like that. This kind of representation is very useful because it actually is decoupled into different properties. And this property may be computed individually in the transformer computation. Right, so that might be next things we want to analyze.